I'll quickly share my screen. And can you see it? Probably I shared the wrong screen.
Yeah, we
Yes, we
were
can.
able to see.
It should be good now.
Yes.
Yeah, thanks, Jia, for the introduction. My name is Amber. I have been working in distributed systems for around 13 years now, 13, 14 years. I have mostly worked in all the cloud providers, essentially, and all the distributed systems, including the metadata systems. That has been my specialization until now. I have previously worked in Microsoft, in Amazon, in Meta, and right now I'm at Oracle. And in all these places, I've been working in distributed systems. So in this particular talk, I want to introduce a well-known problem in distributed systems. It is well known in the fact that in most of the cases, in most of the scenarios we face it, the implementation and the solution to it is generally custom made, and it depends upon the exact use case. But I will be providing the general guidelines and general principles that if we follow, we should be able to solve this problem in a consistent manner. Okay. So these are the few things that I want to cover in this presentation. I'll give a brief overview on how sharding is generally being done, how it is helpful, how it enables a high throughput in a distributed system. What is rename? What is the problem of rename? How it is affected, how sharding affects it, especially how can we solve it, some takeaways, and then we'll have some advanced discussions regarding what we can do to improve a general protocol. There will be plenty of time for Q&A session. And please feel free to interrupt me at any time to ask any questions or to engage in a conversation. I'll be more than happy to pause. Okay, so let me first lay out what sharding is and what do I specifically mean when I call sharding. So in a view of NoSQL database, when we say sharding, means we have isolated stores for data. One cluster of database cannot be accessed by another cluster. It is done for a bunch of reasons. Generally, the main reason is we want isolation, avoiding hotspots. We want to allow higher throughputs, noisy neighbor problem get reduced, our blast radius in case of an event. For example, there is a power outage in the whole state, not all of the data is unavailable. All of this is achieved generally by sharding. In case of metadata systems and high throughput systems, as we can imagine, one of the easiest way to shard is using a string and just a simple hash on top of it. So let's assume that we have a S3 bucket, a bucket in storage for Amazon, which has millions of objects into it. Now, the easiest way to shard this would be if I have a hashing algorithm, I just push in the object's name into it, perform some mod onto it, and find that, okay, X percentage of objects are now living in a particular shard. A simplest, easy way to shard objects. And now my bucket has all these properties. I can handle a lot more traffic. I have the power of all the database shards available to me. Noisy neighbor problem is virtually gone. I can scale as how much as I want and I need. Generally, I can engage automated scaling. My reads are fast, but it comes with a price. And the price is along the lines that if you want to run any aggregation on top of your data, that is generally slow. If you want to do an aggregation of, hey, give me all the objects that start with letter A. And now it means you have to run query on all the database shards. which of course is going to be slower than if you were to run it on a single instance. So this is just a high-level description of how we generally use sharding, how it provides us with a high throughput, what are the advantages we get, and what are generally the side effects of it. Any questions? Anything you want me to focus on? Or I can keep going.
A quick question on the key to the parallel processing. It
Yeah,
seems that if you're doing the generation of a hash, that
yes,
the cluster one could find that the object sought is actually on the bottom isolated cluster N as in Nancy.
yes.
So but that's not shown in your diagram.
Maybe I could make the diagram a little bit better.
Okay, I just wanted to confirm my understanding. Thank you.
Yes. So uh, I can again make it a little bit better, but the idea is along the lines that when you get an object, you run it through a consistent hashing algorithm. Maybe it is just SHA-256 for the object name. We do a mod by, let's say, the number of shards we have, and we get a final place in the whole cluster where that object is going to be. To keep it simple, I'm not considering the fact that we are going to increase or reduce the size of the cluster. Uh, that's further more complexities into it. And for now, we can keep it outside of this scope. That sounds reasonable. Okay, let's move ahead. Okay, so what does rename mean? So like in a file system, when we change a file name, that's a rename. What we expect out of rename is, first, it is atomic. Second, it is transactional. Generally, in a file system, if you think, let's say on Windows, you created a file and then there are folders. That you created a folder, there are subfolders into it, and then there are further subfolders into it. You can atomically change the name of the parent folder. And all the links, they remain intact. Now, the same idea is applicable to a database, but only if the database is not sharded. If the database is sharded, means the parent node lives somewhere else and other nodes live in different nodes. This does not work out of the box. Some of the use cases that folks engage for rename as far as cloud level storage is considered is, let's say, every commit that we are performing in any of our code bases, it is creating a new unique commit ID, which is then going to be ingested by pipelines. And that pipeline, for example, has something called latest. And it keeps on changing as soon as you make a commit. Second is lifecycle transitions. You want to move data from hot to cold. Cold storage is generally cheaper. And if you're not accessing that data often, then you would want to move it to a cold storage. You made a mistake while naming an object, and now you want to update it. That's a rename. You want to run a pipeline where as soon as you create an object, something happens. That's a rename use case. You have a bunch of objects which you want to just change the name of. A student is expected to submit their homework. They uploaded a file called homework submission with a date. Tutor graded it. As soon as they graded, they change the file name. That is also a rename operation. So there are a lot of use cases which have rename as an underneath layer. Here is the interesting part. Like, how is it a problem for distributed systems? And how having data split across multiple shards become a problem for a rename, especially in a NoSQL system. So let's take an example here. Let's say we have this object model. where I have a parent object with a certain prefix, and it has thousands of childs. For example, hypothetically speaking, you uploaded a movie to the cloud, and that movie is uploaded into specific parts. All these childs that we see here are those parts, and they are linked to a parent key. Parent key is the movie title. They are all living together on the same shard since the hashing key was object name. And we would want a faster access for a particular object. So we kept them all on a single shard. Everything was good here. Now let's say I have to rename this object. As soon as I rename the object, it is very likely that it is going to move to a different shard. If it were to remain on the same shard, the problem was very simple. You just update the name, everything remains intact. But if it has to move to a different shard, it means all these thousands of keys have to move atomically to a different destination and to be deleted from the source. We have to do all of this in an atomic manner. Now, a bunch of things can go wrong. As you can imagine, that since we are copying thousands of keys, some would be copied, some are not, something bad happened, network drop, whatnot. Our protocol should have the ability to recover from it. We should be able to move all the data or none at all. So for example, if you uploaded a file in S3 and now you renamed it, you want it to be either the operation is successful or failed. You don't want it to be halfway done. So main takeaway is along the lines that during the rename, we have to move entire object metadata from one shard to the other. It has to be done atomically. Partial moves are not allowed. And we have to guarantee all of this through our protocol. So that is the basis of the protocol that we are going to discuss. These are some of the strong consistency requirements. We don't want duplicates. For example, we don't want source as well as destination to be visible at once. For example, if you are renaming an object from foo to bar, you want either foo to be there or bar to be there, not both. At the same time, we don't want data loss. Well, foo had 10,000 parts. When it was renamed to bar, it better have 10,000 parts. We should not be dropping data underneath. If for some reason our protocol breaks in between because of the network issue, something bad happened, packet loss, we should be able to recover from it. These are just some of the basic requirements for our protocol. Let's talk about some of the failure scenarios that can happen. For example, I'm copying from source to destination. Let's say the copy was successful, but the delete failed. Because rename is along the lines that you are creating a copy and deleting the source. If your copy was successful, but the delete of source failed, now you have duplicates. On the other side, if your delete was successful, but copy failed, you lost the data. Both of these are bad. Now you have, let's say, partial copy. You copied half of the data and something bad happened, maybe network issue, something else, and now you have partial data. That is bad. Or let's say while you are copying the data, since you have to move a large amount of data, someone tries to read it. They should be able to see only consistent results, because if they see inconsistent state, well, they will not be happy. Now, when I said that when we covered the copy plus delete fails across shard, well, why could it happen? And why is going to affect us? Rename is we create a copy on the destination and we're deleting from the source. These operations are happening on different database shards, which means we don't have a single point to maintain a transaction. We generally can't have a transaction across different shards, different databases, two different databases. A transaction is only going to protect us within a same database. Well, there are some exceptions, but I'm talking about the case when that's not the case. All these are the problems if copy plus delete fails. It's possible that we expose the intermediate state. It's possible that the atomic boundary between across different shards is getting exposed because of the intermediate states. All of these are problems for us. Why it is harder in NoSQL? Generally, NoSQL support transactions to a very small number of keys, or none at all. In case of some SQL databases, for example, Oracle, we can have large transactions. We can get 10,000 keys transactionally. We can send it to the destination transactionally, everything good. When it comes to NoSQL, however, this comes with a very high performance cost. And that's one of the reasons that most of the NoSQL database, they don't provide you with a multi-key transactions. Cross-shard atomic commits, these are generally not available in a NoSQL database. Neither we have global clocks. There is an exception, which is Google Spanner, where you can have global clocks, but apart from that, no one is providing it. And more likely than not, each shard is acting independently. Means each shard can have its own downtime. We can have issues talking to it, network drop, packet loss, traffic spikes. Each shard is mostly independent of each other. Any questions? Okay. Okay, now we are going to the interesting part. We are describing the protocol that we can use to copy the data. Protocol is pretty simple. When we are performing a rename, first log the source and destination, read the data from source, write to destination, ensure that read is fully done, mark it as completed on source, then mark the source for deletion, unlock destination. Let's provide a visual presentation for it. This should make it clear. Let's say we have to move objects from source A. We are renaming it and calling it on the destination B. We send a rename request. Hey, rename from source A. And somehow it's landing on a different database shard, which is called B. First thing we would want to do is log the source. That, hey, this is specific object now has a bit flipped, which says that this is logged. This is no longer accessible for any other use case. Next step we do is log the destination. We say, hey, the name B is now taken up. You can't create any other B on the destination. We have logged the source and destination, and we are only going to unlock them towards the end of the protocol. We read all the data. For performance reasons, we would want to read it parallelly. So let's say we have some paginated way to read them. We read them all in parallel. We write them in parallel as well on the destination. Once this is done, we mark on the source that, hey, by the way, this object is now gone. Consider it as deleted. Why we are doing this? Let's say any request that comes on the source and sees the object, now there is an opportunity for source to say, okay, the object is gone, without actually deleting it yet. Why we are doing it? Is let's say I wrote everything on the destination, but I have not said that this object is concrete on destination because something bad could have happened. I still have an opportunity to go back, to revert everything, means restore the source. I have not deleted anything yet. So this just gives us an opportunity to do the course correction, ensure that things are still intact. If something bad happens, we have not passed the commit point, we can always go back. We pass the commit point when we say finalize, that yeah, we have passed the commit point. Let's now ensure that everything is correct on the destination. Let's run all the validations. Let's see everything is good. Then we come back, we delete on the source. Finally, we unlock destination. This means that between these arrows, objects remain locked. However, this gives us a guarantee that now these operations are truly atomic, at least from the caller's point of view anyways. It's possible that we have some transient state in between, but that is not visible to anyone because we have logged both source and destination. This is the crux of the protocol. We call it two-phase protocol generally everywhere. And this is just a modified version of that two-phase protocol for the rename use case. Any questions? Okay, I can move ahead. Or if there are any questions. See someone. Okay. Okay, so what are the design principles that we generally take into account for solving these kind of problems? We want to ensure safety. We don't want to expose any partial states to the customers. Either we say, hey, source is gone and destination is available, or none at all. Nothing has changed. When we move the data, we copy everything, then we run validations when we call finalize. And only when all the validations are done, maybe the validation is as simple as hash of hash for all the parts. If that is matching from source and destination, means we have copied everything. Once all those validations are done, we can delete the source. In order to achieve higher throughput for copying data, we don't have to do it in a serial manner. If we have 10,000 parts, 100,000 parts, I don't have to go in serial. I can parallelize it. All I need to ensure is I stitch all of those parts together in the correct order on the destination. Well, all of this requires me for maintaining a state, and that becomes the bedrock for correctness. I maintain the state in a way that it can be replayed. If my process crashes, if something bad happened at any point of time, I should be able to restart. And I should be able to restart from the step that I am in. I don't want to replay everything. Generally, I want idempotency. For example, if I'm writing something on the destination, something bad happened, or I didn't get a response, I don't know if it was written correctly or not. I would want the ability to write it again and again and ensure that, yes, nothing bad is going to happen. And if I have to recover from a failure, I should be able to recover from previous watermark so that I can continue working from where I left. I don't want to start from the scratch. To put into perspective, let's say I have a file which is 50 gigs. I renamed it. It is underneath stored as a million parts. All those parts are getting migrated from one database shard to the other database shard. Something bad happened, process died. I see, oh, my source is intact, but I do not see it in destination. If I maintain all the correctness behaviors, that is what you would expect. But that also means every time you try to rename it, well, it always fails because it's such a huge file. Something along the lines that you are trying to upload a huge file from your machine to any of the cloud, you may have seen that, yes, not every time the file upload is successful. But generally, all providers have their clients in a way that when you retry the same exact file, well, they know that, oh, this is the watermark. We were able to actually capture half of the file last time. Now we can take in the remaining half. So these are the kind of optimizations that the protocol is supposed to have to ensure.
Amber, a quick question.
Yes, yes, please.
So, just like when you have cache, right? You have cache coherency issue. You want to make
Mhm.
sure that the data that you copied is also available for local use. Do you have any coherency issues here?
That's a good question. So, generally speaking, we want to, well, we have two different problems to choose from. Either we want to have a local caching enabled, which means we read from the cache, or we disable caching altogether when we are moving the data. Both have their pros and cons. In case of this protocol, the assumption is along the lines that we have disabled caching. We are not providing any local cache data reading because it's possible that while I'm moving data, I have moved half of the data here while the half is still in the source. So if I start reading from the cache, it gets complicated because I have to maintain the state across two different databases. And I want that to be minimized. I want to ensure that I keep minimal state, which I have to maintain across databases. Sorry, did I answer your question?
Yes, you did. Yeah, I see. Yeah, that makes sense. Thank you.
Yeah, that's a good question. Uh, and I think depending upon how you want to achieve, there are possibilities that we maintain caching. There are possibilities that you maintain a duplicate copy on the source while everything is copied on the destination. Depending upon which way you choose, I think we can have some sort of caching enabled. Uh, yeah, so for example, here we saw that we are writing a lot of parts in parallel. If we don't maintain a watermark, if we don't know our checkpointing, something bad happened, we'll have to start from the beginning. Generally not what we want. So a good idea would be to have a watermarking and failure tracking. Now, concurrent operations, when we are doing some operations. For example, I'm moving data, and at the same time, someone asked to read it. I think this is the exact question which Sankaran asked. Now, how do we handle it? There are few generally acceptable practices. The one that I have seen being used most of the places is along the lines, we don't return the result for cached objects, or we don't return the result while an operation is happening. We have a couple of options. Either we return something like 429 to the customer that, hey, concurrent modification happening, come back later. Or we hold their request until the operation is completely done and only then return the result. How we do it, I think, and what path we choose, it heavily depends upon the use case we are handling and what are the promises that we have given to our customers. If our customers are okay with handling 429s, means, yeah, since we are performing an operation and we see a temporary kind of an outage, we are okay with it. And that's an option. However, if you have to provide a very strict customer response guarantees, then maybe you want to hold that request, perform the operation as fast as possible, and then return the result. So a few problems that we initially discarded were along the lines that how do we ensure atomicity when the number of shards keep on growing? Well, our number of shards are growing, and now we have to migrate the data, rehash the existing data to new database shards, as well as maintain atomicity for all of our operations. If we reuse the similar idea along the lines that we log the data that we are performing an operation on until that operation is done. For example, we are moving a large amount of data from database shard A to B because of resharding. If you look closely, it would look like, hey, a lot of objects are getting renamed from database shard A to B. So resharding is essentially rename run at scale. And we can use the same exact rename algorithm and continue to perform resharding based upon that. Uh, any questions? Okay, so correctness. This becomes the most important piece. When we are performing such a complex algorithm, to ensure correctness, that becomes the centerpiece. We are moving customer data from one database shard to other, maybe for different reasons. Maybe the customer didn't ask for it. Maybe we are doing resharding because, well, there is a noisy neighbor problem. One customer traffic is affecting all others. So we have to do the resharding. We have to move the objects. We have to do a rename. We want to ensure that everything is correct. Few things we can do pretty cheap is, say, since we have 10,000 parts in an object A on source, when we moved it to B, do I still have 10,000 parts? A simple count-based validation. Object size in bytes, do I have the exact same size on the destination? After that, we can go into a little bit more involved validation algorithms. One of the most used algorithm is Merkle tree-based validation. Just like what we have in Git, we update a file, and as soon as we do it, the root of the Git directory knows that, hey, something has been changed. We maintain a tree-like structure. We maintain the hash of all the objects underneath. And as soon as something changes, the change is propagated to the top. If we do it on the source, means for the whole object A, I have a hash. When I move it over to the destination, I can ensure that, yeah, the whole object hash is same, means the whole tree is intact. Or if there is an issue, I can walk down the Merkle tree, figure out, hey, where things went wrong. I can replay that part, fix that problem. I have all those options available to us. But what it really means is validation is important. And one of the principles that we can use is along the lines, if we can't verify the correctness, or if we can't prove the correctness, then we can safely assume it is not correct. This will ensure that we are never losing the data because it's generally not the data of the organization or the cloud provider. It is the data of the customers which are hosting there. And it would be really bad if we lose the data. For perspective, S3 gives 11 nines of data persistence guarantees. So we can assume like one object in a trillion objects can get lost and not more. So to recap what we discussed so far, rename, we are thinking it as a rename transaction where we are copying the data on the destination and deleting it from the source. We want to ensure we have atomicity in the system, means either the operation fails or it succeeds, but nothing in between, or at least end user should not be able to see it. We want to ensure through our validations that we exactly have no duplicates. If something bad happens, we want it to be able to recover, and we want to maintain a state machine, and we want to persist that state during our checkpointing and watermarking while we are running this protocol. And to ensure that we are not running a centralized coordinator. Because as you would have noticed in the protocol, we haven't have a piece which is centralized coordinator. We kept all the state localized to a particular workflow, which means every object rename process, we maintain the state then and there. We don't depend upon any other process to maintain the state. So this decentralization helps us achieve the scale at a cloud level. Means in a cloud, generally speaking, we can have a trillion of objects stored. and we can be having millions of renames at any given time. So millions of objects are moving across database shards. Shards can be in different database regions. For example, one in Phoenix, one in Asia, and now we are performing a rename. Our data is constantly moving across global boundaries. We want to ensure that we move the data in a reliable, consistent manner. Now, here are some advanced topics that we can briefly touch upon. If you noticed in the protocol, we had a O of N protocol there for moving the data. Means bigger the object, longer it is taking for our protocol to move the data, which is generally acceptable, but of course, we can do better. If we want and our use case demands for it, we can do O of 1 rename. Means we just move the prefix, and now any operation that comes to us, we go to the destination because that's where the prefix lives, that's where the parent node lives, and then we see, oh, well, the parts have not been moved. If we maintain a pointer to the previous destination or the previous source, we can always go there and read from there. This can help us providing O of 1 guarantees. Means at least the rename was done right away. Reads might be a little bit slow since we are still not fully on the destination. What it would look like is along the lines, I had a big movie uploaded to one of my cloud or a big file of 10 TB. I renamed it. It is moving from, let's say, West Coast to East Coast. I just moved the title. I just created a new folder on the destination with the same movie title, but the data is still on the source. Someone asked for it. I saw, hey, the new name, with the new name, it maps to East Coast. Let me go to the East Coast. I see the movie title there. I tried reading it, but I saw, oh, the data is still being referenced from the West Coast. So for every part, I have to come to West Coast and serve it. This is a trade-off that we can take depending upon the use case. There are some other use cases for rename. One of this was a prefix-based rename, like exactly like a directory structure, where you have a parent folder, then a bunch of folders inside it, and then a bunch of folders and files inside it. And let's say you rename the top folder. In a file system, it happens instantly. However, that's not the case for object storage. And more and more of object storage is being reused as a file system these days. Customer wants to run the exact same workload that they ran on their local machine. On the local machine, they had file system. They were able to run a particular workload, which was doing, let's say, renames a lot of times. Now they want to achieve or use the power of cloud. In the cloud, generally, the object storage is cheaper than file systems. So they pick the cheapest system, which is object, and now they want to run the same workload. This is a common use case, but supporting it requires some of the optimizations. Maybe the optimizations of O of 1 is needed here as well. Depending upon different cloud providers, they choose to do it differently. One of the more important ones, let me first tackle that, race condition handling. For example, you are copying the data, and let's say it takes a lot of time to move the data since it was a big file. Someone asked for it midway. Now, how do we handle it? We have few options. We can tell them, hey, go back and come back later when the data move is done. Right now, you're getting 429 means concurrent modification exception. This is generally handled by all the clients, and they would retry. So that's one option. Other option is, okay, the customer is asking for it. Maybe use this opportunity to move the workflow along. Maybe put more resources into this particular object, since it must be important if customer is asking for it as soon as they start renaming it, move this along. That's one option. Other option is, hey, the customer asked for it as soon as they started renaming. Maybe getting this data is more important to customer than renaming. Let's cancel the rename operation, revert back to the original state, and give back the data to customer. So a bunch of options are available. Depending upon the particular use case, we can choose one of them. Now let's talk about the shard invariant. I think this is pretty clear in itself. The object should exist only at one place. If you are renaming it, means you are moving it from shard 1 to 2, it should either exist at 1 or at 2, never at both. If you are trying to move it, don't give internal states to customer. Even when customers are not asking for a strongly consistent state, more likely or not, they are expecting it. So rather give them either the original state or the final state. Any questions? Anything you want me to deep dive on? Actually, we have a Q&A session. Yeah, thank you all for listening to me. Let's open the floor for questions.
So, Amber, question. So, for most of your customers, right,
Mhm.
do they ask that a lot of this data be put on the cloud, and do they do training on the cloud and inference on the edge, or do they do
Yeah.
training and the inference on the cloud?
Oh yeah, that's a very good question and very relevant question actually. So more and more training use cases are coming to us, uh, depending upon different customers. So we have different level of customers. Some customers are running inference in the cloud. Some are running inference closer to them, which, as you just said, that in the edge environments. So as a cloud provider, we don't generally control how customers wants to use us, but we have
I
both
see.
the use cases. Like we can't tell our customers that, hey, you stored the data on us, how you are using it. And with more and more AI and machine learning use cases, we are seeing a big shift towards the kind of usage that we have. So for example, before this big AI shift, customers were very particular about data loss. And that's why we have this data correctness and guarantees from S3 about 13 nines and 11 nines. This is not the case with AI customers or the customers that are running AI use cases. They are okay with some amount of data loss, but what they are not okay with the speed at which they receive their response. So we are seeing a big shift in how customers are using us.
I see.
Daniel?
Yes, I have a question on after the move is completed,
Mhm.
how do you signal all query, all the distributed queryers to now use the database copy on shard B? How, in other words, it sounds like there has to be a centralized figure. You were using the hash to calculate, and even there's still the question of uh, the record. When does it? I guess I'm confused a little bit on how you make that final transition from pointing requesters from shard A to shard B?
This is an excellent question. Thanks for asking it. So there is a client which is making the request for the object. So client is either making a request for, well, source object A or the destination object B. So in the client, we can put a consistent hashing algorithm where the client would know based upon the object name how to hash it and how to figure out on which database shard it's going to live. So client doesn't need to be updated. No one else needs to know. We are not maintaining a centralized algorithm for this. Every client has the same hashing library, let's say, into them. When someone asks for A, they automatically come here on the source shard. When someone asks for B, they automatically go here on this database shard.
Well,
So when
that's it. Yeah, that's
the
assuming though that that's assuming that the clients are in charge of storage destinations based on the name, which is correct,
yes,
which is really a very bad idea designed for a database. You'd want to use a global unique identifier that never changes so that people can change names. But the question still becomes how you must have a centralized source to go from name to GUID, which is the global unique identifier. And that identifier needs to then have live in a place that points from this identifier is located on either source A or destination B. And if you have distributed queryers, in other words, they all have like a copy of this of the GUID database, you need to update all their copies at the same time of the GUID to shard mapping. And that's the problem that I didn't see addressed. You sort of
yes.
you sort of sidestepped it by pretending that the name was the source of the hash, but nobody would ever do that. That would imply that the requester can sort of mess with your database by just providing random names that hash to different values.
I think you asked exactly the question which should have been asked. So yeah, as you said, I skipped past it by laying down that yes, we are routing based upon the object names. Now, generally speaking, that's not the case because now we are opening up to all sort of attacks and whatnot. And generally there is a layer of indirection. But when the request is coming from the client to us here, if we
Yes.
maintain, yes, for every object, let's say we have a UUID created, and let's say we just create a hash of it, and then we have a UUID created. And that hash algorithm that we have for the object is, let's say, internal to us.
Mhm.
I'm not saying that they still can't perform an attack on us. They can still just keep on asking a particular single object to bring down the database by creating a
Isn't it
hotspot.
right? But so every bucket. So I noticed that there are like the blue and the blue, green, orange, and blue and the red.
Yes,
Those are all represent responders to queries made by client requests. But those
yes,
requesters need to be updated simultaneously upon moving from a isolated DB cluster 1 to isolated cluster DB4 so they know where to go. That's the question that I didn't see answered, which is how do you simultaneously, and that's a much smaller job than moving a bunch of data. Do you lock the record and then tell everybody that record is locked when they get a completion of a full lock on every bucket server? Then you can send the update, and that's how you do it.
so we generally maintain a caching of this information, and it is a write ahead cache. So we maintain a cache that, okay, this is going into this particular cluster. When this moves and the request comes back, it follows the same exact path. Now the object is lost, is not there. It's a cache hit. We find the next place where it lives, and then stores the
Oh,
information.
okay. So each individual cluster,
Yes,
when it that's it. So that's how you trigger that the move has been when the
yep,
data has been moved from the old to the new.
yes,
You then mark it as deleted. And then the
yes,
next request for that, regardless of which bucket it is in, will go to the old place and see that,
yep,
oh, this record has been deleted and moved.
yeah,
And so then it'll do a full, like long-term, whatever the big search is at the
yes,
centralized database to find the new location. I got it.
yes.
Perfect. Thanks.
And the reason it works for us is because at least until now, rename is not one of the most time critical operation for customers.
Correct. Yes.
As soon as it becomes, we'll have to find a better way to do it.
Well,
But that was
this
a
sound,
very
yeah, you
insightful question.
no, your plan is very good because the updating to the new location is a very quick operation. It's just a matter of pointer changing as opposed to having to move massive quantity. You're not waiting for massive quantities of data to move. I'm
Yeah.
assuming you could certainly read data in the old location because it has not been deleted until the
Yes.
fully completed and
The
verified
move.
data transfer has taken place, which is
Yeah.
great. I don't see any problem. Excellent. Thank you.
Uh, any other questions? Anything else I can help deep dive? We can discuss.
Not, Jaya.
Yeah, Amber, thank you. That was really a beautiful presentation and it's really knowledgeable.
Thanks for the opportunity. And I got some real good questions asked here. So this was really good. Thank you.
Thank you very much.
Thanks, Amber. Good job.
Thank you, Amber. Thank you, Jaya, for running the meeting.
Yeah, thank you all.
Good presentation.
Have a great evening.
Yeah.
Bye-bye.
Take care.
Have a good
Bye.
night.
Yeah.
Bye-bye.
Bye.